Good morning. Today we're going to wrap up our whole topic of statistics and probability. And keep in mind that that's exactly what this topic is, statistics with probability. The statistics, of course, are finding all of these individual numbers that help represent a bunch of data, whether it's from a sample or predicting it to a population. The probability comes in that when we have these types of distributions, we can then find probabilities based on that type of distribution, whether it's one of our discrete distributions or whether it's our continuous distribution. Most common continuous distribution, of course, is the normal distribution or possibly even the standard normal. So I'm just going to present several examples, most of which you can find somewhere either in the text or in the problem set in the text. So just want to talk through some of these, and hopefully it'll give you some confidence that you can complete the problem set from 29D. So here we go. First, in this case, we have some data of 1,972 rugby players. They have a mean height of 179, very simple to find. Standard deviation of 7. Again, if we had the data, it would be very simple to find. We want to find certain probabilities. The first is the probability of at least, they're at least 175 centimeters. So if I want to take a look at a solution for this, it can be as simple as really rewriting it in terms of our nice probability random variables that we want x to be greater than 175 or equal to because of the phrase at least. And then we're basically just going to use our calculator again, the normal CDF because it's always going to be cumulative, and we want 175, and we then want to go to a very, very large number, and then we have our 179 and 7. Now, the large number that you want to put in there, we can't put infinity, so, put some, 10 to the 99th power, really whatever you want. Variety of things. Any big number is going to give you a value that's close enough to the real answer. And you get about 0.716. Okay, so a pretty good probability there. Now, as far as between 170 and 190, it's the same idea. But if we try to use good notation, we're basically looking for this probability. And you might ask whether or not we need to have some type of is this going to be less than or equal to? Well, because it's between, it should really be less than without the equal to. However, it's not going to make a difference, remember, because the probability that it's exactly 190 would be 0. Now, if we do this, same idea, we'll let it be the normal. CDF, and then we just have to put that range. We got 170, 190, and then the same idea with the mean standard deviation. This case is going to be about 0.843. One thing I think is important with these is we consider what it could look like as a graph. And I'll try to squeeze this in here to see if it can help us make some sense of this. But if I were to make a graph of this function, again, 179 is the mean, so we maybe put 179 here. And then if I go ahead and make my nice normal curve, I know the standard deviation is 7, so up here is 186. That's where we get that 1 point of inflection. And then we get 172 is that other point of inflection. And we know that 68% of the data would lie between one standard deviation to either side. So the reason I'm talking about this is to just give us maybe a pretty good idea that the number that we get from the calculator makes sense in terms of area. So if we want it to be greater than 175, we're talking about right here, all of that area would be believable that it's about 70% of the area. From 170 to 190, 170 is back here, 190 goes even further. It's definitely bigger than 68%. So again, the 0.843 would make some sense. So understanding this visually can maybe reinforce or let you believe that the number that you see from the calculator. Next example. 80% of students should pass an exam. Why? We won't get into that right now. The mean is 62 with the standard deviation of 13. We want to find the expected lowest score. Well, if I want to use some notation to really describe all of this, remember that I can go to my random variable takes on a normal of 62 13 squared. This can basically replace all of these words. All right, so again, make sure you understand that notation. It doesn't do any calculation for us, but it can help with interpreting the problem. So what I'm really looking for is the probability that x is going to be less than or equal to k is going to be 0.2. Now you might wonder, why is that? Because I want it to be at least 80. Well, I could do this first. Maybe call that x of 1, and I want that to be greater than or equal to 0.8, or k to be 0.8. So this might be the interpretation, but remember, when I'm going to use inverse norm eventually, I always have to go from the least value. So in other words, this part of the graph and moving up. And then we know that k is going to equal basically the inverse norm. And the syntax is, what is that area? I want 0.2. And again, you just put your parameters of 62 and 13. And then that turns out to be about 51%. Either as a decimal or percent would work. So if a student gets 51%, they're going to pass. Now, this might seem a little weird that you would even want to do this, but I did know someone that was teaching at a law school, actually, and it was required that their mean was 84%. So they took the data of any test, and that's how they fit it. It makes it a little bit scary that us teachers or people involved with math can kind of do what we want in terms of our grading, but we won't really get into that because that's not quite how we do it here at the high school level. Last problem. Find the mean and standard deviation of a normally distributed random variable x if the probability that x is greater than or equal to 50 is 0.2, but the probability that x is less than or equal to 20 is 0.3. Again, I could make a little bit of a graph to get a feel for this, but this is an example where it's nice to use our standard normal, because we are kind of comparing maybe two different things, but I have to have some connection. So here are some things I can write. From this, if I want to do this, I can write that the probability of x being less than or equal to 50 is going to be 0.8. Okay, over here, it's basically is what it is. The probability of x less than or equal to 20. Well, I'm not even going to write it, because that's already in the good form. Now what I'm going to do is change it to a z. So that z distribution would give me x, that'd be 50 minus the mean over the standard deviation, and that's going to be 0.8. Over here, it'd be the probability of my z is less than or equal to 20 minus mu over standard deviation. Now we can use the inverse normal or a table to basically find this value. And from this, we get 50 minus mu over sigma to be approximately, let me see it here, 0.8416. And then from this one, we get the 20 minus mu over sigma to be approximately 0.5244. Now, I'm not going to finish this algebra for you, but basically what we have is a series or a system of two equations and two variables. Go ahead and make a substitution, do whatever you need to do to solve that system, and you could check it by hopefully finding that mu, or the mean, would be 31.5, and the standard deviation, or sigma, is 22. Seems a little bit off. Can I read that correctly? Yes, that could work. All right. So, 3 examples. One, very straightforward. Here's some data. Find some probabilities based on knowing the mean and the standard deviation. Another one is trying to find kind of a cut score. So we're using the inverse norm. And this third one is we're trying to find this mean and standard deviation of an unknown distribution, but we know some probabilities about the distribution. So maybe the data has found that to be true. So that's the section 29D examples. Tomorrow I will post a worksheet over really all of our statistics unit that you'll have several days to work on, and I'll give you a due date for that when I post it. And then by the end of next week or middle of next week, you'll be given a take-home test over all statistics. As I said, after that, we'll kind of regroup. There are a few other little things that we want to get out there, and topics that maybe we've skipped throughout the couple years, but we'll try to bring some good closure to this course. So you're not only prepared to move on, but you're confident in the things that we've done over the last couple of years. That's it for today. Enjoy the day, and we'll see you very soon.